What's up, boys and girls, ladies and gentlemen? Welcome to Structural MD Podcast, episode 008, Electron Beam Melting. So that introduction was not very professional, but we'll roll with it. Like the previous couple podcasts, again, we're going to cover another additive manufacturing technology, kind of give you the breakdown, the ins and outs, what it's good for, what it's not good for, how it works, some things of that nature. So I know you guys are busy professionals, so I don't want to keep you waiting, so let's just jump right into it. If you had to define electron beam melting, it would be a thin layer of metal powder is selectively melted by an electron beam. The parts are built up layer by layer in the powder bed. There's no real common terms with electron beam melting like there are with other additive manufacturing technologies. The only thing is, if you haven't noticed yet, people in 3D printing industry love to abbreviate words or phrases. So electron beam melting, quick take a guess, is abbreviated, you probably guessed it, EBM. Just something to kind of keep in mind, especially if you're reading a professional journal or any technical paper. They'll often, just say the words once. So they'll say, in the introduction or the abstract, executive summary, whatever that front part of the paper is, they'll spell out electron beam melting, put in parentheses next to it EBM or denote that somehow, and then just use EBM throughout the rest of the paper instead of typing out electron beam melting every time. So how does the technology work? Well, it's really similar to laser melting. The only difference is, you probably could figure that out, instead of a laser doing the melting, it's an electron beam. So like with many metal powder processes, the machine will distribute a layer of metal powder onto the build platform. It's then melted by the electron beam. The build platform gets lowered. Another layer of metal powder is spread on top, and that process of coating the powder and melting where it's needed based on the drawing file or the CAD file that you created. Parts are built up layer by layer in the powder bed, and your process is done when it's done. Electron beam melting does require support structure. It does two things. It anchors the parts to the build platform and the overhangs or the things that would not be supported and would possibly melt due to gravity. It's not melt, fall due to gravity. If gravity was melting things, this would be an extremely weird world. Things would be a lot different. But that support structure, in addition to simply supplying support to those parts and anchors, it also enables heat transfer away from where the powder is melted. So this will help reduce thermal stress and prevent warping. Like many times when you heat up metal, you're going to induce thermal stress and induce warping as you change its chemical. You don't necessarily change its chemical properties, but you change its phase. It's going from a solid state to a more molten or liquid state. As you know, with welding, if you don't tack weld and kind of rotate your weld around, you will warp the metal. Whatever you are welding, it will be warped in the direction that you are heating, i.e. welding. So that's something you want to avoid. And having that support structure kind of acts as a sink, drawing that heat out of the product or the part that you're creating. The build envelope can be conveniently filled by several parts. They're built in parallel as long as they're all attached to the build platform. So you need that starting point, that quote-unquote base metal to weld to or to melt to. So you can't just start it in midair. The one intricacy I would like to add is the parts are built under a vacuum. So they're not just simply built inside of a standard chamber that is open to atmospheric pressures. These parts are built under a vacuum situation or scenario, if you will. When you hear that, just think of dollar signs. It's going to cost a lot more money because there's a lot more technology that goes into electron beam melting. Like with many of the other episodes describing processes, I've also attached a couple videos in the show notes. I went out and found some on YouTube for you guys to look at. Again, it's a rather challenge to describe a very visually rich and engaging process in a verbal manner. So feel free to check out those videos. They'll be in the show notes at structural-md.com/P008. They're not that long, roughly 2 minutes or so. I'm sure you've guessed it by now. This is a strictly metal process. The metals that this process typically handles are cobalt, chromium, a nickel-based alloy, or titanium. They're more of handling expensive metals, metals that are extremely expensive to manufacture. Not your typical like A36 steel or things of that nature. These are more of, I'm drawing a blank on the word, so excuse me. And I don't want to say precious metal because it's not a gold. It's a more expensive metal. One of the reasons this happens is because with typical other processes like subtractive manners, you'd have to buy more material than you really need to go into your part. If you wanted a part that was, let's say, a cubic centimeter, but it had intricacies, had holes and little nooks and crannies, you might have to buy a part that is 2 cubic centimeters or something that's larger to eventually subtract down to that smaller part that you would end up with. But again, you're having to cut away material, so essentially you're buying material that you're eventually just going to throw away or scrap. So it's costly, and if there's a better way to do it, people would obviously be all for it. That other way to do it is additive, because you're only adding the material that you need that actually goes into the part. The rest of that powder is not melted by the electron beam and can be recycled and reused, and that's a whole other conversation for a whole other future podcast in regards to reusing metal powders or unsintered powders or unmelted powders, if you will. So the applications with electron beam melting are really similar to other metal melting processes. They make small series parts, they make prototypes, they make support parts, very similar to what other laser melting processes are used for. Advantages and disadvantages. Nothing in life is perfect. Everything has its pros and cons, and electron beam melting is no different. So what are the advantages of this technology? Well, one of the big ones is it manufactures high density parts, metals with high density. That was one of the big problems that this technology, metal additive manufacturing had in general. They couldn't create very dense parts. There'd be a lot of porousness within the part, and that would not be what's desired. It's not great from a mechanical performance standpoint. Since they now get that higher density, above the 99th percentile, they're getting great mechanical properties out of EBM manufactured parts, which are compared, obviously, to their traditional counterparts. If you haven't picked it up, one of the things that's commonly used as the quote-unquote baseline for additive manufacturing is the traditional production counterpart. However, the part was created before additive manufacturing existed. When you compare laser melting and EBM, EBM will produce less thermal stress in the parts and require less support structure than its laser mounting counterpart. In addition, the other great part about EBM is it has a faster deposition rate relative to laser melting, so therefore parts are built on a much quicker and faster process. Obviously, speed is important because then you can obviously move on to other prints or other projects and keep the ball rolling forwards instead of waiting for a long time to speed up your part. That's kind of why air travel is so cool, because if you can fly from New York to London in, what is that flight, 6 hours or so, versus taking a ship that would take roughly 2, 3, maybe 4 times as long, speed is king. All right, we have to do it. I don't like being negative, but let's take a look at some of the disadvantages. It's just the truth of the game. Relative to other 3D printing technologies, EBM is still slow relative to those, but it's quicker than laser melting. Hopefully you kind of pick that up. This is an expensive process. We touched on the fact earlier that it's contained within a vacuum. It only works with those 3 limited sets of metals. And one of the reasons that it is so expensive, in addition to the vacuum, is the fact that vacuum is just so heavy. Those machines are extremely heavy, weighing well over thousands and thousands of pounds. And one of the things is this technology is only available at the Department of Defense. So as far as I could tell from my research and the people that I've talked to in the industry, there's no service bureau that has EBM as a printing option. Typical other service bureaus, you could choose between FDM or binder jetting and things of that nature. But if you wanted EBM, you can't even pick that because it's only accessible at the Department of Defense. The machines cost well upwards in the multi-millions of dollars, and it just kind of comes with the territory of having that special vacuum and all the other intricacies that go into the machine. And the parts do require a lot of post-processing. And the post-processing comes from the fact that they don't achieve very good surface finishes when compared to laser melting. So post-processing involves a lot of things. It involves removing support structure, getting good surface finishes, and other things of that nature. So whereas you have less support structure to remove, you have more work to do to achieve your good surface quality finish that you are after. So it's kind of one of the things you have to balance. But again, unless you're working for the Department of Defense, chances are you won't be printing an EBM anytime soon. Jumping into the additive slices section, the largest machine to date that I could find was made by a company called Sayaki. It prints in 19 feet by 4 feet by 4 feet. Again, machine has cost $3+ million. And unless you work for the Department of Defense, chances are you won't be seeing it or having access to print on it. I would like to mention, and I forgot to mention before I jumped into the additive slices section, that again, these facts, these figures are up to date as of me talking or presenting them to the podcast. They might change with time. This field is ever changing, ever evolving, and it's extremely difficult to stay up with. There's new discoveries every day, which again, it might be hard to stay up with, but it makes it super interesting and super engaging to interact with. Real quick, just running through the last few figures here. The minimum feature size is 1/10 of a millimeter. Your typical tolerance is plus or minus 0.2 of a millimeter. Again, with that post-processing or that machining, you can improve this or tweak it. Your minimum layer thickness is 0.05 of a millimeter. And your typical surface finish ranges anywhere between 20 and 25 microns. Again, post-processing helps you improve that surface finish. We already touched on the density. It's well above the 99th percentile, often approaching 99.99%. That's all we have for today on EBM technology. Again, if you have any questions, comments, concerns, would like me to come speak to your organization about a technology in particular, or speak to your organization about 3D printing in general, what it can do, what it can't do, just help to kind of get you guys introduced to the technology, see how it could help you, I'm more than happy to come speak to your organization at any time. My email and contact information are all in the show notes at structural-md.com/P008. I hope this helps you guys. I hope this better helps you understand EBM and additive manufacturing. And if there's anything of value that I can add to you, please feel free to reach out. I'm more than happy to help. If I don't know the answer, I will definitely do my best to find out someone who does, or put you in contact with someone who can get you the answer. Until next time, until podcast 0009, I added a few too many zeros there.